Mấy bạn có thấy được cái slide chưa?
Rồi thấy được rồi.
Ok, vậy tôi bắt đầu nha. Thank you the previous teams for your presentations, and good morning everyone. For those of you who don't know me, my name is Ling. I'm in class medicine age 44 and group 3. This is the members in my team. So today I'm gonna bring to you a presentation about nucleic acid metabolism overview. Well, my presentation has 3 parts. First, we're going to metabolism. What is nucleic acid metabolism? And then we move into digestion. How nucleic acids are digested in our bodies. Finally, we're coming to absorptions, how nucleic acids are taken in our bodies. But first, I would like to go through the history of nucleic acids. In 1869, Friedrich Mister discovered nuclein. In 1889, his student, Richard Altman, coined this molecule of nucleic acid. Between 1885 and 1901, Albert Kossel, who was a German scientist, purified the substance and later identified the nucleobases, which are cytosine, guanine, thymine, and uracil. Then, February the 28th, 1953, Cambridge University scientists who were Watson and Crick determined the premortem structure of DNA. And now, what is nucleic acid? Nucleic acids are the polymers of individual nucleotide monomers. As you know before, RNA and DNA are nucleic acids. Each nucleotide is composed of 3 parts. First, a phosphoric acid. Second is a nitrogenous base, and finally is a pentyl sugar, which has 5 carbons in its molecule. If this sugar is a compound ribose, the polymer will be RNA, which means ribonucleic acid. And if this sugar is derived from ribose as deoxyribose, the polymer will be DNA, which means deoxyribonucleic acid. To clearly understand the nitrogenous base, I'm gonna tell you more about its structure and classification. Nitrogenous base has 2 types. Those are pyrimidines and purines. Pyrimidines and purines are the names of the parent compounds of 2 types of nitrogen-containing heterocyclic aromatic compounds. First, purines consist of a 6-membered and a 5-membered nitrogen-containing ring. They fuse together. Purines include adenine and guanine. Then pyrimidines have only a 6-membered nitrogen-containing ring. Pyrimidines include thymine, uracil, and cytosine. Especially, thymine is only in DNA structure and uracil is only in RNA structure. I have done the introduction part. Now I would like to turn to our important parts of today. To start, I'm gonna talk about nucleic acid metabolism. Metabolism has 2 aspects. Those are anabolism and catabolism. First, anabolism is the set of metabolic pathway that construct molecules from smaller units. It is the building up aspect of metabolism, whereas catabolism is the breaking down aspect. Anabolism is usually synonymous with biosynthesis. By many chemical reactions from pentyl sugar, nitrogenous base, and phosphoric acid, nucleotide molecules are created, as you can see here. Anabolic processes build organs and tissues. They help to maintain the genetic information through many generation cells to make human's body exist and develop. And every cell in human's body can synthesize necessary nucleic acid to exist even when the body isn't provided nutrients from the food outside. Next is catabolism. Catabolism is also the set of metabolic pathways that breaks down molecules into small units. It is the breaking down aspect of metabolism, whereas anabolism is the building up aspect. Metabolism is usually synonymous with bioanalysis. As nucleotides can be synthesized, they can also be degraded to waste product and excreted, or can be salvaged as nucleotide component, such as purine can be degraded to uric acid, and pyrimidine can be degraded to ammonia, which means NH3. Catabolic processes are either decomposed to release energy or used in other anabolic reaction. They help to maintain the stability for our body. The breakdown of DNA and RNA is occurring continuously in the cell, so understanding analysis can help to make clear the reason of analysis process disorder. That's all basic things about metabolism. Next, we'll go to the second part of my presentation, that is the digestion of nucleic acid in our bodies. There are three enzymes attending in this process. Those are nuclease, nucleotidase, and nucleosidase. The first enzyme is nuclease, which is secreted by pancreas. It was discovered by Smith, Wilcox, and Kelly, who were working at Johns Hopkins University in 1968, isolated and characterized the first restriction nuclease whose functioning depended on a specific DNA nucleotide sequence. A nuclease is an enzyme capable of cleaving the phosphodiester bonds between nucleotides in nucleic acids, so it is also known as phosphodiesterase. Nucleases variously affect single and double-stranded breaks in their target molecules. In living organisms, they are essential machinery for many aspects of DNA repair. Defects in certain nucleases can cause genetic instability or immunodeficiency. Nucleases are also extensively used in molecular cloning. Nucleases belong to the class of enzymes called hydrolyses. Nucleases are diverse in their functions and selectivity for certain types of nucleic acid substrates. There are many ways to classify nuclease enzyme. It can be classifying depend on active position of the enzyme on the nucleic acid molecule or depend on the substrate. And the most common way is classifying depend on the position. We have two types. Those are endonuclease and exonuclease. If you read some document, you can meet the classification depending on the substrate. I mean RNA or DNA. Then we have deoxyribonuclease and ribonuclease. The next enzyme that attends the digestion process is nucleotidase, which comes from intestine. Nucleotidase plays a catalytic role in hydrolysis process, and it converts a number of different nucleotide molecules. When nucleotidase is involved in catalyzing the hydrolysis of a nucleotide, this creates a reaction as follows. A nucleotide with water forms a nucleoside and phosphate. Within the body, nucleotidase plays an instrumental in the digestive system, facilitating digestion by breaking down nucleic acids. Nucleotidase catalyzes the hydrolysis, separating the nucleoside and the phosphate, so it's considered as a phosphatase. And now it's the last enzyme, nucleosidase, which is also from intestine. The nucleosidases are continually hydrolyzed into nitrogenous base and pentose sugar with the catalysis of nucleosidase enzyme. It's also known as a phosphorylase because it catalyzes a phosphorylation, as you can see here. Okay, to summarize this part, the final products of the digestion are phosphate ions, pentyl sugar, and nitrogenous base. These products then will be absorbed. The absorption occurs mainly in duodenum and jejunum of the small intestine. At the intestinal villus, all nucleic gases are absorbed as nitrogenous base, pentyl sugar, and phosphate ions. Membrane transport proteins will carry the products of nucleotide digestion into epithelial cells from the lumen. Some involve active transport and other involve secondary active transport. Through diffusion, these products are transported from the intestinal epithelial cells across the basolateral membrane into intestinal fluid, and then into the blood capillaries of the intestinal villus. Nucleotide digestion products are transported by the blood circulation to the liver and other tissues where they undergo further degradation. Okay, now let's take a look at this diagram. This is the summary for everything I have talked. We obviously can see that the phosphate is used in the phosphorylation or excreted. Uh, the pentose metabolism is the same to usual glucose metabolism. And the last product of nitrogenous-based metabolism is uric acid, urea, and carbon dioxide. Now I have a question for you guys. So, which products in this diagram will be reused? That's my question, please. Hello?
Hello.
Hello?
Can you repeat the questions?
Okay, my question is, which products in this diagram will be reused?
The nitrogenous base, and the pentose sugar.
Anything else?
And yeah, thanks. That's all.
Thank you for your answer. And my exact answer is phosphate, nitrogenous base, and pentyl sugar. Anyway, thank you. These products that can be reused is phosphate, pentyl sugar, and nitrogenous base. They are reused to synthesize new nucleic acids or glucoside, lipid, or protein. Here. So that's everything in my presentation about nucleic acids metabolism overview. Thank you all for your listening, and now we'll go to meet the next team. Thank you again.
Thank you.
Thank you.
Xong rồi đó mấy bạn.
That's good.
Cảm ơn mọi người.
Hello mọi người.
Wow, hello vậy.
Hello Quyên.
Quyên.
Mọi người có nghe không vậy?
Ông nghe tôi trả lời. Có luôn.
Nghe. Good morning, everybody. I'm Ring from Last YN, and today I will present to you about acid nucleic metabolism. Here is my team. My team has 16 members. My presentation includes 3 parts: 1, 2, and 3. And we move to the part 1 overview. So that you can know furthermore, I will show you a short video. Wait a second.
In today's anatomy and physiology lesson, we will be talking about how nucleases happen. Enjoy.
My DNA and RNA sensitivity.
Okay, that's the overview of digestion and utilization of nucleic acids. We continue. Okay, nucleic acids are nutritive value mainly because of the sugars they contain, namely ribose and deoxyribose. In the small intestine, pancreatic nucleus, DNA and RNAs break down nucleic acid to nucleotides, which are dephosphorilated by alkaline phosphatase to nucleosides. Later are taken up by sodium carbonyl active transport. There are 2 intestinal transporters that refer purine and pyrimidine. And now we will move to the part 2, purine dehydration, and I will show you some steps involved in purine catabolism. The purine molecules AMB and TMB are dephosphorylated into their corresponding nucleotides such as adenosine and guanosine. This reaction is catalyzed by the enzyme nucleotidase. Next, guanosine is converted into guanine by removing the ribose. Then it will be deaminated into xanthine by the enzyme guanine deaminase, while adenosine will be deaminated into inosine, then enzyme nucleosidase will hydrolyze it into hypoxanthine cytophrome. Oxidate reaction will change from hypoxanthine into xanthine by remove one F2O2 molecule. The xanthine is converted into uric acid. This reaction is catalyzed by xanthine oxidase. And the end product of purine dehydration in humans is uric acid. So, how is normal blood level of uric acid? Females from 2 to 5 mg per deciliter and male from 3 to 7 mg per deciliter. The daily excretion varies from 500 to 700 mg. Nucleic acid contains in more in non-vegetarian diet. Nucleic uric acid is very solute in water. Most animals, such as ramas, birds, several insects, oxidize uric acid by the enzyme uricase to allantoin. The allantoin is then converted into allantoate and excreted in some fishes. Further degradation of allantoids may occur to reduce urea in amphibians and to ammonia in marine invertebrates. So, if you have more than 7 mg per deciliter, you will have high uric acid, and it relates to some cases such as goutarthritis, type 2 diabetes, tumor lysis syndrome, Leach-Nyhan syndrome, cardiovascular disease, and the last one, uric acid stone formation. The first one I will tell you about goutarthritis. I also give you a short video. Wait a second.
Gout is an arthritic disease of your joints caused by too much uric acid in your body. Normally, your liver processes various substances in your body, including purines, which are components of genetic material found both inside your cells and in some foods you eat. When your liver breaks down purines, a waste product called uric acid is produced. Your body disposes of this waste through your kidneys, which remove it from your blood. When your liver produces too much uric acid, or your kidneys do not remove enough of it from your body, excess uric acid accumulates in your blood, resulting in a condition called hyperuricemia. Caffeinated beverages affect the waste removal function of your kidneys by increasing your urine output, which eliminates too much water from your body, a condition called dehydration. Dehydration can result in a higher concentration of uric acid in your body's fluids. When the concentration of uric acid becomes too high from any of these sources, it can no longer stay dissolved. The excess uric acid begins to form needle-like crystals inside your joints, most commonly in your big toe. Formation of uric acid crystals leads to an inflammatory response. White blood cells from your immune system attack the uric acid crystals, resulting in joint pain and inflammation. This is called an acute gout attack. If left untreated, elevated uric acid levels may result in lumpy deposits of uric acid around your joint, called a tophus, causing additional joint pain and disfigurement. Treatment for acute.
That is overview about gout. So we continue. Hyperuricemia with induced gout have various potential origins. 1. High fructose corn syrup and table sugar. 2. Video aggression by the kidneys. 3. Fasting or rapid weight loss. 4. Certain drugs such as thiazide, diuretics, and the last, tumor lysis syndrome. So, how many types of goutarthritis? There are 5 types. Asymptomatic hyperuricemia, interval or intercritical gout, chronic to facial gout, septal gout, and the last one, acute gout. And we have some treatment. We can use non-steroidal anti-inflammatory drugs or corticosteroids. And we move to the type 2 diabetes. Hyperuricemia may be a consequence of insulin resistance in diabetes. High serum uric acid was associated with higher risk of type 2 diabetes and metabolic syndrome, including in children. 3 is tumor lysis syndrome, an emergency condition that may result from blood cancers, produce high uric acid levels in blood. Tumor lysis syndrome may lead to acute kidney injury. Treatment includes hyperhydration. 4E Lesch-Nyhan syndrome is a rare inherited disorder, spasticity, involuntary movement, and cognitive retardation, as well as gout. Next is cardiovascular disease. Hyperuricemia may increase risk factors for cardiovascular disease. And the last one is uric acid storm formation. So, how about low uric acid? When you have less than 2 mg per deciliter, and it's related to some cases such as hyperuricemia and multiple sclerosis. And we move to the part 3, pyrimidine dehydration. Okay, pyrimidine is one of two classes of heterocyclic nitrogenous base found in the nucleic acids DNA and RNA. In DNA, the pyrimidines are cytosine and thymine. In RNA, uracil relays thymine. And now I will show you some steps of pyrimidine catabolism. Step 1. Nucleotide to nucleoside. CMB, UMB, and the other side, IMB, are converted into citidine, uridine, deoxythymidine. This reaction is catalyzed by the enzyme nucleotidase. Step 2. Deamination. Citidine is deaminated into uridine by citidine deaminase. Step 3. Phosphorylation. Uridine are converted into uracil. Release ribo 1-phosphate by the enzyme uridine phosphorylase. By the same way, deoxyribo 1-phosphate and thymidine are products of deoxythymidine phosphorylation. Step 4. Dehydration. Uracil and thymine are converted into dehydrouracil and dehydrothymine by dehydrouracil dehydrogenase. In this reaction, one NADPH plus H plus is oxidated into NADP plus. Step 5. Cyclization. Dehydrouracil and dehydrothymine are converted into beta-uridopropionate and beta-uridoisobutyrate by the enzyme pyrimidine hydrolase. In this reaction, the cyclase molecule is converted into glycerol by leaving the covalent bond at a particular place. So, step 6. Deamination. Beta-uridopropionate and beta-uridoisobutyrate are converted into beta-alanine and beta-aminoisobutyrate by the enzyme beta-uridopropionate. The secondary products of this reaction are ammonium ion and carbon dioxide, and the beta-alanine and the beta-aminoisobutyrate. These are highly water-soluble compounds. They may be extracted with the urine, or it may be transmitted to melanin semialdehyde and converted into acetyl-CoA by transamination and hydration process. Beta-alanine and beta-aminoisobutyrate converted into malonic semialdehyde and methylmalonate by transamination process, and it will convert into melanin-CoA by hydration process. In transamination, it will used by aminotransferase enzyme, and the second substrate is alpha-ketoglutarate. The secondary product is glutamate. Dehydration. These two products are entering the part of fatty acid catabolism like methylmalonyl pathway. So I will tell you about some clinic application. The first one is DBD deficiency. This is an autosomal recessive metabolic disorder in which the absence or significantly decreased activity of dihydropyrimidine dehydrogenase (DPD). So that means people with this deficiency cannot break down the nucleotides uracil and thymidine. In infants with severe DPD deficiency, the signs and symptoms may include hypertonia, seizure, autism, microcephaly, intellectual disability, and the last, delayed motor skill. Individuals with this condition may develop like retinal toxicity following exposure to 5-fluorouracil 5-FU, a chemotherapy that is used in treatment of cancer. Because the drugs are not broken down efficiently by people with DPD deficiency and build up to toxic levels in the body. And the last one is beta-uridylropionase deficiency. Loss of this enzyme function reduces the production of beta-aminoisobutyrate. It may impair the function of these molecules in the nervous system, leading to neurological problems such as developmental delay, seizures, and autism. So that's all. Thanks for watching so much. Goodbye and have a nice day.
Thank you.
Thank you.